Okay, so I'll give an introduction, short introduction about Professor Alexandropoulos before we go for the seminar. So George Alexandropoulos received the engineering diploma, the bachelor, master, and PhD in computer engineering and informatics from the University of Patras in Greece, 203, 205, and 2010, respectively. He has held senior and principal research positions at various universities and research centers, including the Mathematical and Algorithmic Science Lab of Huawei Technologies in France and the Technology Innovation Institute at the United Arab Emirates. He's currently an associate professor with the Department of Informatics and Telecommunication, School of Science at the National and Kapodistrian University of Athens, Greece, and also adjunct professor with the Department of Electrical and Computer Engineering at Illinois, Chicago. His research interests span the general areas of algorithmic design and performance analysis for wireless networks, with emphasis on multi-antenna transceiver hardware architectures, full duplex MIMO, active and passive RIS, ISAC, millimeter waves, and terahertz. He has been editor and is currently editor of many IEEE journals and transactions. He also won several awards, but I'm not going to go into the details, otherwise I'll take all the time of the seminar. So thank you, George, for accepting the invitation, and the floor is yours.
Thank you, Eva, for this nice introduction. Thanks, everybody, for being here. So let me share my screen and we do go directly with my talk today. Tell me if you see my slides.
Yes, we can see it. You put it full screen, perfect.
Do you see them changing?
Yes.
Okay, perfect. So we can directly start just to make it on time. I have a rather ambitious plan today. So my talk is going to be around this whole trend of extremely large multiple input, multiple output systems. And I will present you some recent results from my group related to this paradigm of integrated sensing and communications, as well as a direction which actually fascinates us a lot and has to do with the actual consideration and optimization of MIMO systems for performing inference over the air. And hopefully I will explain today what I mean with that. Before going to the actual presentation, I will do it from the beginning to acknowledge two projects where the vast majority of the work we're going to see today are included and have been actually performed within their framework. The one is called TerraMeta and has to do with terahertz reconfigurable intelligent surfaces, and which is about to end, is spanning its last year of phase one SNS projects, and another one called 60 DISAC, where DISAC stands for Distributed Intelligent Sensing and Communications, and we are very close to the midterm review of this phase two SNS project. So just a few things about where we stand. I guess we might have diverse attendees today. So this is a slide that actually has to do with the actual trends and the use case scenarios by IMT. ITU actually is the main organization of SIG-G. So in a way, what you can see here is that the trend is to extend this triangular of these three use cases: eMBB, enhanced mobile broadband, massive machine-type communications, and ultra-reliable and low latency, to, of course, much more demanding numbers. This doesn't mean that we have achieved them in 5G, but still we're trying to target much higher. And the inclusion of these three new edges, as you see there: ISAC, integration of AI, which is one of the two things, together with AI, to be incorporated in 6G, and probably these are the two key items. And of course, this notion of ubiquitous connectivity with mainly with terrestrial and non-terrestrial communications. Of course, we want to have sustainable networks and this security and trustworthiness everywhere, which are actually quite demanding things. Now, in terms of, let's say, more specified targets, I'm not going to specify numbers here, but these are some discussions that have been taken from Ericsson. This is a very recent discussion on requirements and targets for 6G related to network energy efficiency, this reduction in the energy consumption. One way to do it is by reducing the transmission of always-on signals, long battery lifetime with these wake-up signals that we can use in order to provide power-saving mechanisms. The increased capacity using new spectrum, which is actually the heart of my presentation today, And of course, we want to make it without this densification. These small cells didn't really go through. And in order to achieve this increased capacity, the trend is to go even more massive in terms of massive MIMO technology and the incorporation of new centimeter wave spectrum. Coverage extension, of course, especially for cell edge users, uplink data rate improvement, because it is a provision that we're going to have use cases that are quite demanding. And now the uplink is going to be one of, let's say, the Achilles heel of the upcoming networks, where we need applications like XR and AI agents. And of course, high precision positioning. There, AI is expected to play a huge role. And of course, this integration of sensing and communication, where the difference compared with position, now we're talking about sensing of devices that are not connected to the network, and we want to do this with the actual communication network infrastructure. So this is actually the timeline related to 6G. So by the end of 2030, actually, we want the first deployment of the 6G networks. You can see here some couple of phases. So in a way, we are in the actual beginning of all the mature, let's say, discussions related to 6G. And here, just going a bit back, just to see the actual, this mapping of the direction towards 6G on the releases of 3GPP, where currently we have finalized release 19 and already discussions related to release 20, the actual items, technical items that are going to, and technologies to be incorporated. And my focus today is on one of them related to the physical layer. Another key item that is actually happening, and this has been one of the hot things also in the upcoming the calls related to our field of communication networks, is this incorporation of new bands, since we have realized that this FR2 is quite problematic. Terahertz, it doesn't seem to be the way for 6G, although in some specific applications it's quite relevant. So we have this incorporation of these upper mid bands, 7 to 24. I will emphasize to 7, 15 here, which are expected to provide wider area capacity by supporting smartphones, smart cities, automotive, and other verticals, to provide this scalable boundless XR user support in wider area, and of course the high resolution sensing that I mentioned before. And let me discuss a little bit this connection between higher frequencies and MIMO. So with my higher frequencies, millimeter wave up to terahertz, this FR2, which are FR3, sorry, which are the upper mid bands that I mentioned before, they're also relevant. They're much larger bandwidth expected to be provided there compared with FR1, which is the dominated band in 5G right now. This extra bandwidth can be used for providing high resolution sensing, and with comparison with the actual increase in the number of antenna elements, we can have this higher angular resolution. So with this combination of higher frequencies and multiple antennas, we can get this dual angular and range improvement in terms of resolution. Of course, the goal here with the combination of these XL MIMO systems and large frequencies that can be really good for sensing and more elaborated services related to data rates. We can profit of estimations related to range, velocity, and angle, and we can use them for actual applications, but also for optimizing the physical area. It seems to me, and to many people up to now, that let's say this sensing trend is mainly for optimizing the way we design the networks, and we're still thinking of the actual application, the actual market for this sensing that we're providing. So let me go directly now to an actual demo and a demonstrated actually XL MIMO transmitter that you will see here, called the GigaMIMO, having this 4096 antenna elements actually put down by Qualcomm, as you see in this figure, operating at this 13 gigahertz in the upper mid-bands that we mentioned before, this new band of FR3, working together with FR1, as you see on the bottom of the slide, providing actually high beamforming gain. You see this 33 dB, and this has been actually tested over the air in San Diego this year. So with this introduction, let me go directly to, let's say, the meat of my presentation today, some stuff about XL MIMO architectures, and then I will talk about how we could use XL MIMO to boost ISAC, and then hopefully I will make it on time to provide this new application of XL MIMO for over-the-air inference. So starting with MIMO, some very basic stuff. The main, let's say, idea and the pioneering thing related to MIMO has to do with the fact that we can use multiple antennas, antennas that we can tune certain properties of them. For example, you see these weights there, could be the currents that is flowing towards this antenna. And effectively, this can help us creating actually beams with different shapes, beams implying the way that the signal propagates in the 3D over the air. This is quite cool because we can use those beams to provide beamforming gain, meaning boosting the received SNR at a certain direction, or even use them to provide multiplexing gain. Multiplexing with these degrees of freedom, these spatial degrees of freedom provided by the multiple antennas at both sides, transmitted the receivers, in order to increase data rate at the end of the day, multiplex more data streams or serve multiple users simultaneously in comparison with other schemes like TDMA, FDMA. So we have three layers of optimizing our systems. In terms of architecture, there has been a lot of discussion nearly 10 years ago about architecture that have been put down on implementing those multiple antenna systems. We have this fully digital array architecture where we have each antenna element being attached to a dedicated radio frequency chain. When we talk about the transmitter, this RF chain will have a power amplifier, a mixer, and a digital to analog converter. Vice versa, when we're thinking about the receive side, the receiver chain would have a low noise amplifier, again a mixer, and an analog to digital converter. Of course, this has the complexity, equal number of antenna elements with a number of RF chains, and you see the power amplifier here, which is one of the major issues if we're thinking about higher frequencies, resolution. These are things that determine the actual performance of this device, plus the actual cost. So here you see the case of the fully connected case. As I mentioned before, all RF chains connected to all antenna elements. We have these phase shifters here. This can mimic actually the fully digital precoding, which is the most expensive, let's say, but this is the upper bound performance that you can get in terms of beamforming gain or multiplexing gain at the end of the day, right? And this is the equivalence between the number of RF chains that you should have in order to mimic the fully digital case. Now we're going to the partially connected case. Please see this connection of only a subject of antenna elements exclusively to a separate reception RF chain. And all these architectures have been used, as I mentioned before, for various purposes, to multiplex different users, to send multiple streams to a specific user, or even a couple of years ago in LTE Advanced, this coordinated beamforming, incorporating actually co-designing, co-optimizing various transmitters with multiple antenna elements in order to implement, let's say, a multi-antenna transceiver in a decentralized way. There are various issues with that. I saw my dear friend Angel before discussing about the fundamental limits of cooperation, but it's still there, a version that one could think of using multiple antenna systems, multiple antenna systems in order to realize multi-user beamforming. Of course, we have also the massive MIMO concept, where this is the pioneering thing that happened a couple of years ago, incorporated with E5G, which has very simple multi-user beamforming and channel estimation process in order to have, at the end of the day, pencil-like beams towards a specific user. There are all these issues with the pilot contamination, if we're thinking about massive MIMO with multiple cells, etc. I'm not going to dig into these details. Let me proceed with the architectures. A couple of years ago, please see also the references. 2020, there was this proposal by Samsung on this multi-hybrid architecture, transceiver architecture that incorporates, as you see here, a baseband unit, reception RF chains, sorry, transmission or reception RF chains, and this being connected to metasurface-based antennas. Or on the right, you see the version where you have a typical hybrid analog and digital. In here specifically, you see the partially connected architecture, where very close to the actual antennas, this is the transmit part, we have a metasurface lens. This is called recently a tri-hybrid antenna architecture, but I wanted to emphasize that these discussions can be have been out there for a couple of years ago, profiting of the fact that you can have metasurface antennas with very large number of elements to realize very efficient beams at the end of the day. And this is where it goes, this paradigm, this concept of the dynamic metasurface antennas, where exactly what is happening here, the vision is to have metamaterials of tunable responses, which at the end of the day have frequency selective responses. They can effectively provide a phase shift on the impinging or the outgoing signal. And these guys are usually printed on a waveguide, with this waveguide having input or output ports to be connected to a reception RF chain or a transmission RF chain, respectively. In these papers and in this figure, you see an attempt to try to actually model the actual performance that takes place within this so-called microstrip. So the difference with conventional antenna arrays, that is now in terms of having, let's say, multiple dipoles and phase shifters, now the idea is that you're having all those elements which need, of course, to lie on a waveguide which has the actual role to feed the signal to either a reception or a transmission RF chain. And this is exactly what I'm trying to describe in this slide, where you see in subfigure C an 1D waveguide connected at the end of the day to a transmission or reception RF chain. What we can manage is that we can manage those elements to place them very close together, sub-wavelength the distances. They operate as resonators at the end of the day. There is, of course, apart from the tunable responses, which are effective phase shifts of these elements, there is some propagation that happens within this microstrip when you feed it from a specific part. And this propagation actually includes phases which need to be incorporated and accurately modeled. And the good thing at the end of the day, which is one of the major advantages compared with conventional antenna arrays, is that you can actually have these frequency selective response. You can design those elements to have a response on a wider band. Although the analog beamforming with conventional phase shifters, usually you fix it, and this is the actual phase shift that will take place in the entire band. So going further here, I would like to emphasize that you see this is very similar to this architecture, where we're thinking actually on this architecture on the left, having RF chain. These are the ports connected to those metasurface-based antennas, right? And those elements, you can actually, they're cheap, they're easy to fabricate. You can actually implement quite many of them, and you can place them quite close. Mutual coupling can be there. We will discuss later on related to that. And there is also another trend that has been discussed very recently, is that, okay, now instead of I'm going to this stacked intelligent metasurface, this is very relevant to this part, at least this figure. Please focus on this part on the right, where you see this three-hybrid version. You have the digital part, processing part, the analog processing part with RF chains. You have conventional antenna elements, and you place nearby a metasurface antenna. In this case, instead of placing a metasurface antenna, the vision is to place layers of metasurface antennas, which at the end of the day, the vision of that paper is to remove certain portion of the actual signal processing for beamforming or other purposes we'll discuss later on today that you want to put down, not on this analog or digital part, but remove it entirely in this so-called wave domain part. That's why you see in this figure, this low precision DACs and low precision ADCs. Why? Because actually you can optimize this cascade version of metasurfaces in order to compensate of losses that, of course, inevitable losses that will take place by lower, let's say, the complexity of the analog and the digital part. I'm not going to dig into more details. You can see this really very recent book, which is available for pre-order, related on technologies on reconfigurable intelligent surfaces, various hardware architectures. So I'm not going to talk about RISs today. So let me try to also bring up this very fresh paper by Heath and his team, Robert Heath, talking about this three-hybrid MIMO antenna architecture. Tried to convince you before that this is something that has been discussed a couple of years ago as well. So the idea here is, again, what we discussed before, having this, the three-hybrid stands for the digital signal processing part. Please mute yourself. There's someone that is interfering. Thanks for that. That the analog part with RF chains, you could have antenna elements here with phase shifters, and you could have a last portion that is implemented with either these switch pattern antennas, dynamic metasurface antennas that we mentioned before, or even parasitic arrays. And these parasitic arrays, this brings me back of a couple of years ago, working together with other colleagues on this notion of this electronically steerable passive array radiator antennas, where the main principle is that you have one active or multiple active elements which are actually being surrounded by parasitic elements. Those elements are called parasitic because there's no actual power source feeder that drives them. Instead, there is a tunable load. You can tune this load, and at the end of the day, profiting from the mutual coupling, you can create, again, beam patterns similarly to having actually all the antennas being active. Of course, for this specific implementation, you need mutual coupling there. Otherwise, this does really not really work. Okay, there's also another version, this load modulated antenna arrays, where instead of relying on mutual coupling, there you don't actually need it. This is an architecture presented a couple of years ago. By the way, I'm not going to talk today on the issues, the disadvantages and problems with this architecture. Of course, you can see these papers, but we can take it offline with a sparse on low modulated arrays. They are not actually implemented today because they have several issues, but I wanted actually to let's say enrich this discussion, this very recent paper, because they're related to the parasitic antenna arrays. So there is this load modulation version that I mentioned before, where now there is a matching network. Again, there is this notion of tunable elements, but in this case, you don't need mutual coupling. It can work without mutual coupling. And this has actually triggered especially this sparse that I mentioned before, this very recent concept of dynamic scattering arrays, where again, you need this mutual coupling, where at the end of the day, the vision is again to have active elements and having parasitic elements. They can place randomly in the vicinity of the active elements because you need actually mutual coupling in order again to profit of this much lower complexity multi-antenna XL MIMO technology, given the fact that you could increase this number. These are basic scatterers of tunable responses here to realize beams with nice properties, or even computation. So the vision there is to use them for over-the-air signal processing. So certain computation to happen directly in this domain of the way that the signal propagates between those among those elements. Now, before proceeding, I would like to sketch that when we're talking about XL MIMO, large number of antenna elements, and before I discussed mainly about this enabling technology of metamaterials and metasurfaces, or reconfigurable scatterers, scattering points, scattering antennas with reconfigurable properties, which are cheap to implement and you can scale their numbers. When we're going into large number of antenna elements at higher frequency, there is this near field that kicks in. Right, this interplay of large antenna apertures and high frequencies actually leads to near field communication, which is a new paradigm compared to the far field, where we have this angular based beamforming. Since in this case there is this curvature of the signal that you see here, right, and this spherical waveform is not negligible and needs to be incorporated within the actual design. And this is a basic figure here trying to explain this. There has been this so-called Rayleigh distance defined by the maximum phase error caused by assuming a plane wave across the array. And what happens with this curvature is this signal, if you see there is a transmitter here and the receiver, the receive antenna array, you can see that there is this d distance of the actual bore side that happens here, the straight line, and this d prime. If this distance actually you see here is not zero and it's below P over I, the beamforming gain that you have there, then we enter into the Rayleigh distance that actually defines explicitly with this, the intention of this metric was to exactly identify the transition point between the near and the far field regime. So this Rayleigh distance corresponds, as I mentioned before, to the limit where the phase error, by assuming this equality, is below this pi over 8. But of course, when we're thinking about multiple antenna system, recently we came up with actually a study where we understood what is very relevant is this notion of this beamforming gain. So you need to understand where this beamforming gain actually, how does it change between far field and near field. And just to be more specific, what we tried to address in the papers that you see on the bottom of this slide is how far the far field model remains accurate without significant beam forming gain loss, or in a way, alternatively, what is the distance up to which the far field beam forming can be applied without preserving the intended gain. So we came up with some analysis here that under normal incidence, there is this new distance here, this RDF, has to do with this beamforming gain, where beyond this distance, this RDF, the far-field approximation introduces less than 3 dB error on the beam design, compared to accounting for the waveform curvature. So this actually signifies this transition between the near field and far field when you're having actually large antenna systems and you realize beamforming. This analysis has been made both for ULAs, UPAs, lossless and lossy DMAs in the papers, a very recent paper presented in the last EURASIP, very relevant to the EURASIP community. And just to give some numbers, just to understand now why we're getting into the XL MIMO era. So consider this Rayleigh distance that we mentioned before, defined by this D 2 times D square, when D square has to do with the actual surface of this 1 times 1 antenna size, this antenna aperture, square antenna aperture. If we're operating at FR3, specifically at 7 gigahertz, this Rayleigh distance is around 93 meters, 9.3. It is for the new distance that I presented before with the beamforming gain, much closer. At 24, with the Rayleigh distance is almost around 300 meters, 32 it goes with the metric that we provided before. So you can see that in actually distances that are quite large, we're operating in the near field region. If you go to even higher frequencies, if we end up in beyond 5G, let's say this 300 gigahertz, this will be around half a kilometer for the more strict metric that I mentioned before. And also you need to think that if we keep the aperture size fixed, this element count, when you're having inter-element distance of lambda over 2, gives this number. So you have this 2.2 times 2 in the power 10 in the power of 3 at 5 gigahertz number of elements, and then we go to millions of elements at 300 gigahertz. So certainly we're talking about an XL MIMO area if we combine also those frequencies, right? And if we're thinking about this operation of the near far field that I mentioned before. So let me present you some works related to XL MIMO for ISAC boosting, and I will go directly to the system model. So we're considering in this work a wideband bistatic system where the transmitter has a uniform planar array, which is implemented by a DMA. There is a fully digital multi-antenna receiver. There are G targets in the vicinity of these two guys, and we want actually to send pilots, the OFDM, in different subcarriers, right, widespan in frequencies from the DMA transmitter in order to localize the presence of these guys in their vicinity. So for the DMA, we assume that you have NRF, number of disjoint microstrips, with each of them having n epsilon elements. These are microstrips 1D1s. This is the total number of antenna elements, and we have an NRX having fully digital, as I mentioned before. This is MR is the number of receive antenna elements. This is actually the notation for the actual digital combining matrix that the receiver is actually using. This is the system, and in the system we assume that we only know a certain uncertainty region between for every target within the system. So as I mentioned before, the transmission is of OFDM pilots, T pilots over K subcarriers, repetition over M capital consecutive frames. There are some conditions that need to be met in order to be able to find those G numbers. You see here this condition. And this is the pilot that we send, as you see here, and we send it with a hybrid analog and digital precoding. We have this digital precoder by this notation that you see here, this FM. Hopefully you see the hand that I'm trying to move. And there is this analog beamformer here, which is the configuration of the actual DMA, its analog part. And the resulting transmitted signal is given by this cascade product of matrices. You see the signal, a digital precoder and the analog precoder, a typical constraint on the power that we're transmitting those guys, and just a notation of putting down all these digital precoders for the overall numbers of frames, this Mi capital that you said before. Here you see the received signal, what is being received at the multi-antenna receiver here. This is the channel that we're using. As you see here, this channel, we have this actually multipath channel. We have those paths equal to the number of scatterers that you see here, of these targets that we want to identify. We assume there are no other scatterers within the system, only the targets, subcarrier frequencies, the complex channel gauge that you see here, the delays, the angles, azimuth, and elevation, as well as the steering vector and transmitter receive steering vectors. So we have the TX being positioned in a specific place, orientation angle of this transmitter, and there is also this delta T. We assume that there's a clock offset as well between the transmitter and the unsynchronized receiver that we want to estimate as well. And this is the definition of the uncertain area. So we assume that we don't know where the target is, of course, going to estimate it, but we assume that we know an uncertainty region per each of these guys. We're now extending with a case where you don't know per guy, but you know for all of them. Here you see the model that we have used for the DMA analog beamforming matrix being given by this expression. This is the analog beamforming matrix. Just to emphasize, there are a couple of matrices here. Just I want you to draw your attention. This PSA that models the propagation from each transmit RF chain to the metamaterial elements. You see how is this guy is defined. We're using this recent model of this paper that you see on the bottom of this slide, where actually it incorporates the Green's function in order to model the propagation within its microstrip. There is also another matrix that models the mutual coupling that you see here, mutual coupling between elements of the same waveguide, right, of the same microstrips, or mutual coupling between elements of different microstrips. Again, there is a Green function incorporated. And there is also this QTA matrix, which is actually a diagonal matrix representing the actual reconfigurable elements, right, of this DMA system. These are the guys that we can play with, and we assume, as commonly happen in practice, that these are chosen for a codebook. I mean, each element has a number of discrete responses. It cannot change continuously. There are varactors there, but for the varactors to operate in the continuous space, you need actual power supply for this one, which is quite tricky, quite demanding to implement it. I mean, I'm not going to dig into details to that, but we can discuss. So long story short, the emphasis of this paper, just to make it on time, is that we have actually used an approach through Woodbury's formula in order to approximate. First we started expanding this inverse that you see here for the analog beamformer of the DMA by this expression, and then we have applied, due to the fact that in dense antenna arrays there is this condition that holds, that you will see the result for the approximation later on. Applying Newman series, you can actually write this inverse by this expression as you see here, and now you can choose the number of terms to use in this summation. If we keep only the two terms, then we will end up with this expression that you see here, where you can easily recognize that this inverse has been removed, which makes our life much, much easier. This is an example where we actually have tested the square node difference between the approximation that I mentioned before with this Newman series with a number of terms. How many terms? You see 2 and goes up to 20, for various frequencies from 8 to 28 gigahertz. The emphasis on the FR3 band that I mentioned before. For a DMA with 4 microstrips, 32 elements per microstrip, and you can see here that we have quite good results even by using only 2 terms in this Newman series approximation, which motivated to use it later on in the whole analysis. We have provided also a PEB analysis, which is actually important for the formulation of the problem that I mentioned before. These are the channel parameters. We don't know the channel parameters related to the targets. Please recall that. We don't know the offset there related to the clock and synchronized transmitter, the receiver. These are also the location parameters. We don't know the actual location of these guys. So profiting of this received output, you can write it by this expression here, which is actually ends up the received signal in baseband to be a complex Gaussian actually distribution here, this vector with this mean and this covariance matrix. You can easily write down the Fisher information matrix. You can even incorporate some prior knowledge that we have done here related to the clock offset that I mentioned before. And using this Fisher information matrix, you can actually formulate the position error bound, and using some mathematical tricks there, some linear algebra, you can write it as being linear in terms of this. This is the product. This F includes the digital precoding matrices. So we can call it covariance of the digital precoder at the end of the day somehow, right? So you can write this theme as a linear function of this x. And this is actually the focus of the design. So we focused on actually optimizing the transmit and the analog and digital beamformers. We don't really care about the receive beamforming part. We have used a similar, as you see here, way as we do it on the transmit part, but the emphasis is on the DMA here. And this is the design objective. We tried actually to design the analog and the digital beamformer at the DMA transmitter in order to minimize the maximum of the position error bound for the given the uncertainty of the position of the targets that we know beforehand, right? And under the constraints of the related to the actual operation of the DMA and of course the power constraint. Here, in order to solve this problem, we discretized those uncertainty regions. We actually computed the position error bound for all the points of the grid in this discretization, and will solve this problem in this way. In order to do that, we followed a couple of approaches. I don't have time to dig into the details. So there is a codebook-based approach where, in a way, we try to find the closest DMA beamformer, which is closer to a 3D fully digital codebook, incorporating this, as you see here, beams dedicated to the actual points of the grid, as well as differential beams that are known to perform quite well. We have solved this problem. You can see the details in the paper, coming up with a final expression about the analog beamformer of the DMA. We have also used another approach where, instead of optimizing the actual theme, we optimized an upper bound, a lower bound. We had a lower bound of the theme, so we optimize a bound, a worst case PB, as before. The formulation, you see it here. I don't have time to dig into the details. This problem has been solved. And just to show you some results, considering two scatterers, some here considerations related to the uncertainty region, a large uncertainty region, a smaller uncertainty region. We also played with the discretization in terms of points of those elements. These are two scenarios here of covering the uncertainty regions. We have also the link between the clock bias and the PB. So the PB across the plane here, the XY plane, where what we see, what we notice at the end of the day, that this direct CRB minimization provides the best performance, but also the approximate, the low complexity solutions perform quite well, illuminating the actual area, because our goal at the end of the day, guys, just to emphasize, is that to create the right beams illuminating the uncertainty areas in order to get the reflection at the receiver and being able to estimate their position. And there, the number of elements plays huge role. Why? Because you can have these refined areas with the actual beamforming. We don't want pencil-like beamforming here. I want to emphasize, we want to cover the area as better as possible, providing the larger gain as possible toward that area. So we have extended, let's say, this framework on the notion of now, before it was only sensing, here it is simultaneous communication and sensing by using a full duplex XL MIMO transceiver realized by DMAs, where we have a DMA at the transmitter and at the receiver right now. And the system operates as follows. There is a user, there are targets. Assume that you know the position of the user through 5GNR positioning. Now you send data to the user. This data, you know this data because you are a full duplex guy at your reception part, and you try to estimate through the reflection of the data the actual scattering points where this data, this signal, information bearing signal, where had scattered actually the scattering positions. This is what we're trying to do here. This is a formulation. So again, we try to optimize now in this way. There is self-interference. So we want to treat also the self-interference. In full duplex, the problem is that your own transmission has much stronger power than the reflection that we'll get from the downlink signals to the targets that are within the vicinity. Of course, there we need to think of the link budget, but all the investigations that we have done were in link budgets that actually we can estimate those guys. Of course, we can estimate due to the design, not only that they're not far away. Here, we're trying to actually opportunistically maximize the downlink rates with, as you see here, we have a position error bound that has to do with the positions for any a priori knowledge of the targets. Again, we can use a similar approach, and this is what currently we're extending with the area-wide PEB that I mentioned before with the uncertainty. And here, I mentioned opportunistic before because actually you try to do as much as you can with the downlink rate in your free design parameters, which are the analog and digital beamformers of the transmit DMA, as well as the receive DMA, right? And there is this D capital, which is the self-interference digital cancellation matrix at the full duplex XL MIMO node. By certifying that you meet this position error bound threshold, you have this typical power constraints, but you have also two constraints that deal with the residual interference after analog and digital self-interference cancellation. In this actual paper, we showcase that you don't need analog self-interference cancellation. With these beams and this XL MIMO, you can only have a digital cancellation unit, and by the appropriate design of the beam forming, transmit and receive beam forming, you can actually meet this analog self-interference residual metric, right, without requiring to incorporate analog taps or auxiliary transmitters to treat self-interference in the analog domain. Some results that showcase certain performance, and we have actually in this paper working both with conventional hybrid analog and digital beamformers. This is the terminology fully connected phase shifters, and this PCM starts for the partially collected metamaterials. These are the actual DMAs. Again, we can see here that with this easy scaling of the number of metamaterials, you can get really good results. And this beamforming, again, this beamforming design actually does the job irrespective of your operating in the near or far field. On the left, you see the case where in the optimization for doing to the actual user to provide data on the downlink results on this beam focusing, where when you're operating in the near field in different distances, you create this angular-based beamforming, the far-field beamforming, which is the output in both cases of the same algorithm, irrespective of the channel model that we use. Another result here that shows the PEB performance over an area, and at the end of the day, signifies the role of the different free parameters of the system, again emphasizing that with the DMAs, those metamaterial-based XL MIMO, you can have much better performance meeting these both metrics, right? This position error bound for a certain rate threshold. So in the amount of time, let us sketch a little bit this new notion of using XL MIMO as ELMs. Eva, please interrupt me when I need to stop, but I prefer to make it describing this example, which we find quite fascinating, right? So let me go on this part. And recently, we have been started looking actually a MIMO system and the actual transformation that the wireless channels can provide as a form of computations that can happen over the air. So having said that, I mean, assume that in this noiseless MIMO channel in the baseband, we have this representation, this received signal Y equals the channel matrix A times the transmitted signal X. And if you actually be more careful here, you will notice that there is a similarity with the feed-forward linear layer of deep neural networks. Though here we have this H, which is completely uncontrollable. This is the channel for us when we're talking about MIMO, but it can still be useful somehow. We will see it later on. This noiseless equivalence that I mentioned before goes also in the highest scenario regime. Otherwise, you need to have the normal noise here, the AWGN. And there is something else which is quite critical when we're thinking about DNNs. The proper DNN linear layer has a non-linear activation function, right? Plus a bias term, which we don't really see it in this actual very basic baseband representation of a MIMO system. Now, a MIMO system can also have a linear combiner. Linear combiner means that you can have a matrix here. In general, it could be a matrix, could be a vector in special cases, where you actually, there's a baseband representation again, where you operate, right? You multiply effectively this received signal vector Y. So this output of the linear combiner, the zeta, provides an additional controllable operation of the received signal, right? Which is actually can be realized in the analog RF domain. How? If you do analog combining that we mentioned before, right? So long story short, what I'm trying to convince you here is that a properly designed MIMO, an XL MIMO, you will see why we need an XL MIMO here, could be used as a means to implement a DNN directly over the air using some components in the analog RF domain at the receive side. And let me go into more details now, treating this MIMO as a way of realizing learning over the air. So MIMO can be treated as a two-layer DNNs with the reason that I provided before, under the following conditions, these three conditions, that we are in the large antenna regime, and you will see realize why. This enters us into the XL MIMO era. We need also to have analog combining at the receiver with nonlinear elements. And you will see later on that we need sufficiently rich scattering on the propagation environment. With metasurfaces, this scattering, we can make it just to be proactive here and try to get you into the way we have been thinking this overall process. So we believe that this XL MIMO, such an XL MIMO system, can be casted to the framework of these celebrated, actually well-known extreme learning machines that actually serve as analog universal approximator computer. These are machines where this universal approximation has been proven. What are the key elements here when thinking about an XL MIMO as an ELM? Now we have the phasing coefficients, right? Those phasing coefficients can act as random projections of the information bearing transmitted signal. Therefore, each element can capture a separate representation of the input data. I'm talking about each receive antenna element. The rich scattering that I mentioned before can offer this highly expressive representation space. The combining weights at the receiver can actually select which representation are useful for the inference task. And we have that nonlinearities, right, are required at the receiver. This is something that we don't have in typical MIMO system, reception of MIMO systems. Otherwise, we will have a serious problem in approximating universal function. We can only approximate linear function. So what we would like to do here with these XL MIMO LMs, the XL MIMO LMs can actually perform closed form training, can easily adapt to dynamic fading, and we don't need actual processing at the transmit side, only analog combining at the reception side. I will show later on. We can train them in closed form for reasonably sized data sets. It can easily adapt to dynamic fading. Why? Because when the channel changes, we only need a few number of fine-tuning steps to readjust the weights, since the training and inference due to this closed form that I will show you later on can happen easily within the channel coherence time. We don't need processing at the transmitter. Transmitting only sends data with analog modulation, and we only need analog combining, no further digital processing. And let me go exactly into the details of that. Here you see the basics of an ELM. So in an ELM, consider you have a data set, right, of input target pairs. These are the input. You see a vector, D dimension. This is an arbitrary dimension of the actual data. And these are the target. The target could be a feature that we want to extract from data. Suppose that you want an inference, you send an image, and you want to understand that within the image you have a dog, for example. In ELMs, we have k hidden nodes at the first layer with random coefficients. We place them in this matrix here. You see this dimension D of data and this k that has to do with the hidden nodes. And we have also this B of size k that are the biases that I mentioned before. We need also an activation function G that needs to be arbitrary and nonlinear, needs to be bounded and infinitely differentiable, as well as convergent. And with these, we have also k trainable weights on the output layer that perform this weighted averaging on the outputs of the activations, as you see in this expression. G activations of the hidden nodes processing the input data plus the biases, right? And we can end up into this expression. So the actual T here, which is the target, iota F target, is being given by this operation of the actual input, right? This dimensional input you see here. G function activation of this linear operation times those weights, which are the trainable weights. And this is the figure of the extreme learning machine as a single hidden layer feed-forward neural network of a hidden layer size K. These are the K here, the K weights that you have, right? We have the random coefficients, A's and B's. You will see the mapping with the MIMO case later on, and the trainable weights. And let me try to here to explain you easily. You can see this paper, how we train an ELM. Easily, to find those weights, you can formulate an MSE objective like here, where this MSE objective, you have this G matrix, the output of the activation function as you see here, right? And we have also this T that include the target values. You can easily solve this problem. This is the closed form expression for this MSE objective, this minimization. And there is the universal theorem that tells us that if the random coefficient within this A, recall these are the A's that I mentioned before, the random coefficients of the hidden layers, if these guys are random and IID with infinite support, then for any valid nonlinear activation function, there exists a hidden layer size K, this K, the number of weights, right? Smaller than the number of pairs in the training data set, such as this LS solution gives an arbitrarily small error. By the way, have in mind that this K at the end of the day will be equal to the number of the RX antennas that we will need. So what we need this K to be large in order to make it, but finite, right? And this is where XL-MIMO kicks in. So for this XL-MIMO LN, as we call it in this paper, what we need is to apply a nonlinear function to each received signal component. All the rest that I've shown before, and you will see the equivalence in the next slide, can be performed by the typical operation of a MIMO system. Soft thresholding, actually at each kth RX RF chain here, can happen via the RAPS model. You see here a typical model for this amplifier for nonlinear active elements given by this expression. Here you see the plot. And with this very simple model that actually describes the operation of power amplifier, especially in the nonlinear regime, you see that very closely matches that of a sigmoid activation function. So we can think of actual elements at the receiver side that can perform this nonlinear activation, which is actually needed to do this mapping presented in these slides between an actual ELM and an XL-MIMO system. So you see the equivalence. This is the end-to-end MIMO reception in the first bullet. By the way, all the analysis in this paper is on real channels, the proofs of the theorem, etc., for the actual complex channels that we have in communications, while communications is doable, and we were actually extending right now. So consider that we have this real channel here. This is the signal that the antenna, and at the end of the day, you can write those output, the linear combination of the analog combiner, just an analog combiner that you need here by using the RAPS model before for the nonlinear elements is given by this expression. And you see the jack tag position exactly on the second bullet with the equivalence, right, between the XL-MIMO ELM and the actual ELM. So you see the colors here showcase the jack stack position between these two versions. So an XL-MIMO system can be seen as an ELM, where now the number of the weights equals to the number of antenna elements. The combined signal that you have at the output of the combine of the receiver plays the role of the ELM's output. Those components that you see here that are being transmitted by the transmit antenna, the number of transmit antennas needs to be equal to the number of the size, the dimension of the actual feature, actually the actual data that you want to send. I'm just going back just to show you related to that. And this H plays the role of the random hidden layer. So the actual channel performs this equivalence with the ELM. The activation function I mentioned before do this nonlinear operation, and we have the analog weights, which are the weights that we need to train at the end of the day. I'm not going to dig into the details. You can actually prove that this proposal of seeing the proposed XL-MIMO system, XL-MIMO ELM system as an over-the-air inference equivalent of an ELM, of a digital ELM, we have proven that it actually performs universal approximation for certain conditions. One is the entries of this channel to BIID from a continuing probability distribution satisfied under uncorrelated Rayleigh-Fane conditions. If they are correlated, we need to extend this analysis. We're working on that. And condition number 2, you want this activation function to be infinitely differentiable nonlinear function, bounded, and their limits to infinity to exist, satisfied for a certain actually value of this alpha. This is a free parameter of the actual nonlinear model for, for the reception element that we have used. I'm not going to dig into the details in the economy of time for the train, actually the complexity of that. What you need to have in mind is that this LS-based solution can happen quite fast, which is actually really can be used with this closed form solution to do training. So you can have fast retraining when the challenge changes. And this is the actual process that you need to do. You start with an optimal solution from the past channel. Then you use mini batches of a certain size, meeting this constraint, and repeating this LS solution on each mini batch, and then you update this combining vector. These are the tunable weights that you need to perform when the channel changes, and this is the actual training that can happen on channel coherence time. Some results showcasing on different data set sizes and different features, medical data, actual digits here, and manufacturing data. The proposed actually Excel MIMO ELM achieves equal performance to its fully digital version, and we have also very close operating with a DNN benchmark, this MLP requiring iterative training. In the high SNR regime, we see that this proposed framework achieves nearly optimal performance, validating the exclusion of noise in the theoretical treatment. Even in some reasonable numbers, the accuracy is quite good, as you see here. And here we see a result where we see the role of the multipath richness of the channel, and we see that when we are in rich scattering conditions, the performance it's much, much better. And of course, if we want this to happen in practice, we need somehow to ensure that we have we operate in rich scattering position, or somehow we create rich scattering positions. So these are the things that we're working, extending this work on designing programmable metasurfaces for wave domain low linearities and combining. So we want to design actual elements to receive for the XL receiver antenna array to incorporate non-linear functionalities. We're working on multi-layer DNN architecture. Actually, see here you saw a 2-layer architecture, and ULM is a 2-layer DNN. We're working on combiner optimization for doing more than one operations, where actually we have an idea of doing simultaneously inference and achievable rate maximization. And also we're working on inducing rich scattering in channels by incorporating multifunctional RISs in order to meet all, with all these bullets, all the elements required to actually cast an Excel MIMO system to an Excel MIMO ELM that I mentioned before. So Eva, I don't know how much time I have. Probably I could skip this or just spend 5 minutes.
I would suggest we leave it here, and we open for questions so that we have also some time.
Maybe Eva, give it just 1 minute if possible, only 1 minute.
Okay.
Just to show that in this work, and I'm not going to say anything else, that now we're not treating the channel as a way of realizing over the air this inference that I mentioned before. Here we just, it's another approach where we incorporate metasurfaces within a channel, typical metasurfaces, an RIS, actually a transmissive RIS, or multiple cascade RIS, a SIM, with the actual goal to realize a heterogeneous neural network end-to-end. We call it metasurface integrated neural network. Why? Because we're having encoding a neural network at the transmitter, decoding neural network at the receiver. We have also layers that are implemented over the air within the channel. And we actually want to optimize this end-to-end for edge inference task. And what we saw at the end of the day is that you can trade off here the complexity of the layers. You can actually move more layers to take place between the channel and the receiver, or between the transmitter and the receiver, realizing at the end of the day edge inference with lightweight IoTs. That's the plan at the one of the two sides transmitter of the receiver. So this is the 2 minutes that I needed at the end of the day. So Eva and all, thank you for that. You can see the details also in the papers. I'm looking forward to your questions. Thank you.
Thank you very much, George. I'll stop the recording because we usually don't record the question.